I'm absolutely delighted to be back at LSE. I was an undergrad many years ago here, and I used to come to Sigma Club feeling completely clueless about what was going on. Little did I know I would be invited back to give a talk someday. So I'm very, very grateful for this opportunity to share my work in progress. So I am going to talk about perpetual motion machines today. And in particular, I want to ask what it takes to rule out them in general relativity. So in this talk, I'll begin by explaining why it is intuitively difficult to talk about energy conservation in general relativity. I'll introduce a distinction between energy balance and energy conservation, and we will apply this distinction, these two different notions, to general relativity locally and globally. Then I'll address some existing concerns about gravitational energy before we move to the question of why not a gravitational perpetual motion machines. And there I will defend an account of energy balance, which will allow us to rule out perpetual motion machines. Now let's first start with a very simple question. When do we talk about energy conservation? We talk about energy conservation for isolated systems. If the system is not isolated, why would energy be conserved? Now, when we talk about energy conservation, we're also concerned about the dynamical evolution of the system. So in classical mechanics, the conserved charge is defined along the trajectory of motion. And immediately, you might be able to see that energy conservation is quite tricky in general relativity, because in general relativity, in some sense, isolation is in tension with dynamics. Consider, for instance, a box moving in space-time. In classical mechanics, we know the movement itself, actually, we take for granted that the movement of the box itself does not break the space-time symmetry. But this is no longer true or strictly true in general relativity because matter is coupled with space-time, so any movement of matter disturbs or perturbs the space-time a little bit. Now, what is an isolated system in general relativity? Well, what is an isolated system for in classical mechanics? Actually, we can take, for instance, a box of gas thermally sealed, and we get something that's close enough to an isolated system. But in general relativity, there's no gravitational insulator. You cannot just enclose gravitational effects within. The best you can do is to move far away from the gravitational source and hope that their gravitational effect vanishes. And this can be done through asymptotic flatness, which we will talk about in a little bit. There is, however, a kind of conservation equation in general relativity. It is known as the covariant conservation equation. But it is a consequence of a mathematical identity and Einstein field equations. It doesn't really provide dynamically informative insight. So it doesn't link an initial state to a final state in a very dynamically informative way. So in a sense, where you might be able to see that we're caught in bind, the equation that we can easily write down, the covariant conservation equation, is not something that we actually want when we talk about energy conservation, but the equation that we actually want when we talk about energy conservation requires isolating systems, which general relativity seems to resist. And in this slide, I will make a distinction between energy conservation and energy balance. The distinction is roughly this. I'll explain more later, but the distinction is roughly this. Energy conservation applies to closed systems, and energy balance concerns energy transfer between open systems. So in this context, energy balance accounts for the balance between the matter and gravitational field. And this is where the debate about gravitational energy comes in. Many have voiced their views about gravitational energy. People who adopt some version of gravitational energy include Einstein, Hoefer, Pitts, Reed, Gomes, and Rovelli. Gomes and Rovelli actually are realists about gravitational radiation in particular. but I'll group them under the realist camp. Now, on the right-hand side, we have people who are skeptical and eliminativist about gravitational energy, including Infeld, Schrödinger, Rosen, Hoefer, Duerr. And the line might be blurry, so in the middle, I put people, I list people who I understand to be skeptical or cautious about gravitational energy. Now, the eliminativist would say, or they would often say, that gravitational energy lacks certain property. I'll explain later what these properties might be. So it is not real. Now, if gravitational energy is not real, then there is no energy balance between matter and gravitational field. Conclusion goes, there is no energy balance in general relativity. Much of the existing debate focuses on premise one, and in this talk, I'll instead try to offer a reduction argument. If there were no energy balance in general relativity, then gravitational perpetual motion machines would be possible. But before I present my argument, we need to first clarify what I mean by energy balance. Now, in the manuscript on special relativity, Einstein introduced this equation, which we know to be the Poynting's theorem. And he described this equation as an energy balance of the of electromagnetic for electromagnetic fields. So here I'm using the conventional notation where U is the energy density, and S is the energy flux, and E dot J is the rate per unit volume at which energy is transferred from the field to charged matter. In other words, the change in field energy within the volume is balanced by the net field energy flowing out across the boundary of the volume and the energy transferred from the field to charges inside the volume. And then Einstein said this balance relation can turn into a conservation law if the field strands vanish permanently at the boundaries of space. And this is what I take to be an isolation condition. While it is common to say the Poynting theorem is itself a conservation law and to use energy balance and energy conservation interchangeably, Einstein is careful to note that a conservation law only follows after we impose an isolation condition that makes the boundary term vanish, so that no energy enters or leaves the region. That is, to get a conserved quantity, balance is not enough. You have to kind of imagine a hypothetical boundary, right? And this can be done if the fields fall off sufficiently far at spatial infinity, which you actually would always assume in Noether's theorem. We always implicitly in the derivation, we always assume that boundary term vanish. Or this can also be achieved if the region is enclosed by a perfect insulator. And in this case, it would be a perfect conductor that makes the electric or magnetic field normal to boundary. Now, maybe you think this distinction between energy balance and energy conservation is kind of trivial. Isn't it true that we can always, whenever we have energy balance, we can always imagine kind of a hypothetical boundary such that the field vanishes or the boundary term vanishes? I think that is right for classical mechanics, but this assumption is no longer trivial in general relativity. And that's exactly why talking about energy conservation is no longer easy in general relativity. Besides Einstein, a few authors also use energy balance in a way that is not simply interchangeable with energy conservation. Muller, for instance, describes the familiar energy balance of classical mechanics as the claim that the rate of change of connecting energy equals to the power. Poisson emphasized that for radiative systems in electromagnetism, energy is not even conserved, but instead satisfies the balance relation. And Pitts calls the covariant conservation equation in general relativity a balance equation. We'll talk about that in a little bit. To my knowledge, no definition, no standard definition is provided in the literature. Therefore, I stipulate an energy balance statement relates energy change in an open subsystem to balancing terms. And with an additional isolation condition, a balance equation can turn into a conservation equation for a closed total system. Now, you might think that isn't this just a local continuity equation? Isn't energy balance just capturing this idea of local continuity equation? I want you to resist that thought because in electromagnetism and general relativity, energy balance also arises in a non-local and coarse-grained way, where one relates energies in one zones to energies in other zones. So in radiative problems, for instance, it matters whether energy carried by waves at a large distance is balanced by a corresponding decrease of a near zone energy at retarded time. In such cases, balance is not associated with so-called local divergence freeness, but it is a relation between energy losses and energy gains across different zones defined using matching techniques. Okay, now let's try to apply this notion of energy balance in special relativity. Let stress energy tensor T mu nu be the stress energy tensor associated with some system of interest. The balance relation can be written as follows, where F mu is the full force density exerted by the given system on the external system. You can pick your favorite stress energy tensor here. I picked electromagnetic stress energy tensor. You can write it down, and here we'll have Lorentz force density. And we can rewrite the electromagnetic balance equation as follows, where if we take nu to be 0, then we do recover 20 nu. Now, from this balance relation, one can obtain the conservation statement in at least two ways, I think. First, one can say in absence of charges and currents, the stress energy tensor of the field, electromagnetic field, is conserved. Alternatively, we can say, let's treat the field and charge matter together as a total system. Then a conserved total energy follows, provided the system is isolated, that is, the flux through the boundary vanishes.
Sorry, just to clarify, this one not assuming the Einstein equation here for the expression of the stress energy.
In this,
like, I guess it's not 100% clear to me why it doesn't always vanish, that expression, say in the absence of charges and currents, but I thought like just geometrically the Ricci tensor always vanishes.
Yeah, in special relativity, it vanishes. So you can always guarantee that.
But sorry, I mean the gradient of the Ricci tensor also in general relativity just by geometric arguments vanishes in the sense of the covariant derivative.
Yeah, the covariant, in general relativity, we'll get to that. The covariant conservation of the.
Oh, sorry, you're just looking at special relativity. Sorry.
Yeah.
Okay, but then I see. Sorry, you're not assuming the Einstein equation. You're just doing.
Yeah, I am just. Yeah.
Okay, thank you. I was super confused.
No worries. Right. So here we're at special relativity, but we are. I think this is what you wanted to ask. Okay, let's move to general relativity. Now, as a consequence of the Bianchi identities and Einstein field equations, here we go, we have the covariant conservation equations. But this equation holds everywhere, to borrow Nick Hockett's phrase. It is a very important equation, right? But interestingly, it's not that dynamically insightful, because without additional structure, it does not link any initial state to a final state in a way that yields a physically meaningful conserved quantity. And many authors have noted that. Landau Lipschitz, for instance, said, this equation does not generally express any conservation law whatever. And Einstein, Hoefer, Duerr, and many others also said similar things. Now, one might note that if we move things around, we can write this equation this way, and it takes a form. It always looks like a balance equation from special relativity. And I think that is understandable because in special relativity, gravitational effects can be modeled as force, but in general relativity, gravitational effects are encoded in Christoffel symbols here. And indeed, many authors do refer to this equation as the balance equation. I will, however, in this talk, keep referring to this equation as a covariant conservation equation because everyone can agree covariant conservation equation holds in general relativity, but not everyone agrees that it should be interpreted as a balance equation. Now, as in electromagnetism, there are two potential ways, two potential routes from here to conservation. One is for matter itself to be independently isolated, and this may hold locally effectively or globally when the spacetime emits Hailing vector. And the other is for matter and the gravitational field to form a collectively isolated system. It holds in asymptotically flat spacetime, and we will examine these conditions in turn. Now, it's hard to clarify the problem of energy and general relativity without making a distinction between local and global. Often, local in general relativity and differential geometry just means a point and its neighborhood. But when we talk about energy conservation, it doesn't really make sense to me to talk about a point, because a point is just an event in space-time, and conservation is about dynamics, and dynamics requires extensions in space and time. So here's my definition of local region. A region counts as local, just in case the second derivatives of the metric can be effectively neglected. As you may be able to tell, this is motivated by the existence of local Lorentz frame. Locally, we can make any metric Minkowskian up to first order. There are many ways to show this. Fletcher and Weatherall has a recent paper on this. My favorite way to show this is simply do a degrees of freedom counting. So you can compare the degrees of freedom you have in your coordinate transformations with the degrees of freedom imposed by metric and its derivative. So at zeroth order, you have more degrees of freedom in your coordinate transformation. At the first order, the degrees of freedom exactly match, but when you move to the second order, you run out of the degrees of freedom in your coordinate transformations, and it turns out that at some second order curvature comes in, so you no longer can make metric Minkowski at the second order. And but you can always do it up to first order. Brown and Knox suggests that what counts as sufficiently small in general relativity is context dependent. And in this context, we can actually specify the size of the region over which spacetime can be treated as approximately Minkowskian. Why? For a spacetime region larger than this, the approximation of local Lorentz frame breaks down. And physically, it should make sense because the stronger the curvature is, the smaller the region in which special relativity remains a good approximation. So it is not about how small we can make the region, but about how small it needs to be for the approximation to hold. Now we've clarified what we mean by a local region, we can turn to local energy conservation. There are two ways to think about it. First, we can say in a sufficiently small region, the metric can be treated as effectively fixed and approximately Minkowskian throughout that region. That is to say, locally, back reaction and curvature variation terms are suppressed. But we're ignoring, we're neglecting the second order contributions, and that the matter dynamics is to a good approximation invariant under local time translation. This, I think, aligns with how Vincent Lamb thinks about it. One typically relies on a background structure with sufficient symmetry for local ordinary conservation to hold. Alternatively, we can say along a time-like curve, we can introduce Fermi normal coordinates such that Christoffel symbols vanish, so you have covariant conservation. reduced to ordinary conservation. And this, I think, is how Patrick Duerr thinks about it. The energy momentum full current along free fall trajectories is locally conserved. We might think that the second interpretation might be better than the first interpretation because the second interpretation doesn't invoke a notion of background. From the perspective of idealization, I think they are on a, I'm not going to get into detail here, but I'm happy to answer any questions about that if you are interested. Okay, now beyond local analysis, defining the total energy globally in generic spacetimes is very difficult because, as I mentioned, it is very difficult to carve out a genuinely isolated system. But there are still two cases when we can talk about. One is when matter itself is independently isolated, and the other is when matter and gravitational field form a collectively isolated system. Let's first look at independent isolation, that is for matter itself to be independently isolated. I personally find it helpful to always illustrate with like an easy toy example from classical mechanics. So let's start with an idealized pendulum. No friction, right? There you have a time-independent Lagrangian, and you can derive a conserved quantity through Noether's first theorem, and that conserved quantity is defined along the equation of motion. Importantly, the system evolves in a fixed background. That's a very important assumption I've made in classical mechanics. And that the pendulum's motion does not itself break the time translation symmetry. And just like conservation holds, when Lagrangian is time independent in classical mechanics, global conservation holds when the metric is time independent. And this is the same as saying space-time is stationary with a time-like Killing vector field. And then we can also find a conserved quantity defined along the trajectory of a freely falling body. In this case, the space-time, again, serves as a fixed background. I'll call this condition independent isolation, just to highlight that matter itself is independently isolated in this case. Why does stationarity matter here for isolation? Because space-time is time-independent in this case, and in that very sense, effectively independent of matter. This is not metaphysical independence, however. One can still hold the Machian view that the metric ultimately depends on the matter, or we can say metric is determined by matter, but the metric is time independent or stationary here exactly because the matter is stationary. So one can write this condition down either as the metric being time independent or as the lead derivative along the Killing vector field vanishes for this case. Now, the familiar image of a body moving along geodesic and Minkowski spacetime actually relies on a very important idealization because any physical body is not a test particle. So whenever you have a matter moving space-time, it perturbs the space-time, however slightly, the space-time is no longer Minkowski. So strictly speaking, you can't have anything moving in Minkowski space-time, right? So this type of global energy conservation described above, when we have stationary space-time, is really highly idealized, and when it is practically useful, only holds approximately. And Eric Hurel also pointed this out. The smallest speck of dust, the tiniest bit out of space in only one spot in the entire space-time precludes the existence of a Killing field. However, this is not the end of the story. A useful comparison can again be drawn in classical mechanics, between a realistic pendulum and an idealized. So for a realistic pendulum, the total mechanical energy is only approximately conserved, and that approximation depends on timescales. And if we consider the dissipative terms, the effective Lagrangian governing the pendulum does involve explicit time dependence. So the Hamiltonian is no longer conserved, rather it is balanced by a dissipative term. We know that energy is not conserved for the pendulum, realistic pendulum in this case, but it's fine because we know the realistic pendulum is not an isolated system. If we say enlarge the system we're considering, right? If we imagine that we include not just pendulum, but also its environment, the support, the resulting thermal degrees of freedom, the air molecules around, what appears as energy loss from the pendulum will be exactly balanced by energy gain elsewhere. So in this case, despite the absence of time translation symmetry associated with energy conservation via Newton's first theorem, we can still make sense of energy balance. In what follows, I'll argue that a similar structure of reasoning can apply to the interaction between matter and spacetime. When the realistic pendulum interacts with its environment, conservation fails. And similarly, when matter and space-time interact dynamically, stationarity fails, and matter energy is no longer itself conserved. However, if we try to enlarge the system we're considering, if we enlarge the boundary of the system, maybe we can find energy balance. And this, I think, can be done through asymptotic flatness. When a spacetime is asymptotically flat, there exists a coordinate system in which at spatial or null infinity, the metric takes the following form, the Minkowski metric, eta plus some correction. And as you move far away from the source, approaches to Minkowski metric. Asymptotic flatness can be defined without appealing to any coordinate system through conformal compactification, but for the purpose, it's suffice here that we can just say that to have a asymptotically flat spacetime is just to have spacetime to approach Minkowski metric, spatial or normal. I'll call this condition collective isolation. Now, interpreting asymptotic flatness as a condition of isolation is widely adopted in the literature. I'm just adding collective here to signal that it's matter and gravitational field together here being viewed as a total system. Now, asymptotic flatness is also connected to the peeling behavior of the Weyl-Curvature tensor. In particular, Weyl-Curvature tensor can be further decomposed into Weyl scalars, and each scalar dominate different regions. So if you have a binary system emitting gravitational field very close to the binary system, you'll have a kind of Coulomb type effect dominate, and as you move away from the system, if the system has quadrupole, you'll have the gravitational waves at a far distance, you will have gravitational waves dominate. So this is just what we would expect the same phenomenon to happen in electromagnetic fields. So far away from the source, one may write the metric in terms of Minkowski metric plus a perturbation term, H here. And we can rewrite the exact Einstein field equation with Ricci tensor linear in this perturbation H. And here, so this is nothing tricky, we're just rewriting the exact Einstein field equation, and the pseudotensor pop up here. The pseudotensor basically captures the second order contributions and higher order contributions. So you're just rearranging them and group things on different sides based on their orders.
What are you ended up calling the pseudotensor here?
So this is the small t mu is the pseudotensor. What we're doing, this is the exact Einstein field equation. What we are doing.
But why is it pseudo? Sorry, and not.
Okay, yeah, we'll get to that.
Okay.
The reason it's pseudo is because it doesn't transform like the tensor.
Oh.
Yes, and that's the problem. That's why people People say it's not real, but this is what I'm going to focus on. And you're very good at predicting what I'm going to say. Yeah. So with a bit of algebra, one can show that the pseudotensor and the stress energy tensor together will be ordinary conserved. This is not covariant conserved, just ordinary conserved. Weinberg interpreted Einstein as well, but Weinberg interpreted this pseudotensor as the energy momentum of the gravitational field. I want to emphasize here that this is a good interpretation if we limit ourselves to asymptotically flat spacetimes, because it's only in an asymptotic flat region it is natural to treat the stress energy tensor together with the pseudotensor as describing an effectively closed system, and thus speak of conservation. For radiative systems, this term, the pseudotensor, represents gravitational wave G. And this dovetails the local picture. Recall that in local analysis, we're neglecting all the higher order contributions. And here in weak field expansion, radiative contributions appear precisely at the order where the matter-only conservation ceases to hold. So when the system with the stress energy tensor loses energy to gravitational radiation, the energy doesn't just disappear, it travels with the radiation available for absorption elsewhere. Now let's move to the existing concerns about gravitational energy. So far I tried to motivate energy balance argument, but energy balance relies on this very charitable interpretation of gravitational energy, and one might wonder whether such interpretation is justified. Indeed, Hoefer said that actually there's no need to make up a story about where energy has gone, when a system loses it. And there are many reasons why one might say this. One is because gravitational energy is not generally covariant. Right? The pseudotensor is called pseudo because it doesn't transform as a tensor, which means for any given pseudotensor, one can always choose coordinates in which it vanishes. And you might think that this is not that bad because there are things in general relativity that are also not tensors, but still they're meaningful, they're helpful. For instance, the Christoffel symbols, we can always find a coordinate in which Christoffel symbols vanish. But it seems that the problem here is more serious. That is, the pseudotensor is not a geometric object. It doesn't have the transformation, it doesn't obey the transformation rules that a geometric object would. This is noted by Duerr. Moreover, gravitational energy is not unique. That is, you can find infinitely many gravitational energy momentum pseudotensors through a kind of notice second and superpotential procedure. And these worries feed directly into one of the longest running debates in general relativity. Do gravitational waves carry energy away from the systems that emit them? And even Einstein changed his mind twice on this issue. The most famous argument for energy balance or for gravitational energy was first presented at the 1957 Chapel Hill Conference. When it was first presented, it was actually an argument for the existence of gravitational waves, but it can be easily modified as an argument for energy balance. So here's the case. Consider a rod with freely sliding beads. As gravitational waves pass through, the beads oscillate, generating heat through friction, but heat requires energy, and that energy must come from somewhere. The conclusion goes, the system emitting gravitational waves loses energy to gravitational radiation, which does work on sticky beads, producing heat. Since heat is an objective physical effect, gravitational radiation cannot be dismissed as a mere coordinate. This was first presented by Feynman, but it showed up first in print by Bondi, so it's also known as Feynman-Bondi sticky Pete thought experiment. Here are two completely different reactions. One is exemplified by Carlo Rovelli, who thinks gravitational waves are just like electromagnetic waves. He said a strong burst of gravitational waves could come from the sky and knock down the rock of Gibraltar, precisely as a strong burst of electromagnetic radiation could. On the other hand, Hoefer said it is possible to view energy loss by gravity wave source as a genuine loss without insisting that energy is still around somewhere. Similarly, energy gain in a gravity wave detector could be thought as a genuine gain without having to say the energy existed somewhere beforehand. And I will summarize this argument against energy balance as follows. Premise one, gravitational energy lacks property X. And here property X can refer to general covariance, uniqueness, geometrical character, or localizability. So these are all features that we know and we can agree that gravitational energy does not have. Now, if gravitational energy is not real, then there is no energy balance between matter and the gravitational field. And the conclusion goes there is no energy balance in general relativity. Pitts and Reed have argued that neither non-covariance and nor non-uniqueness undermines gravitational energy. And here, however, I will offer a reductional argument. If there were no energy balance in general relativity, then gravitational perpetual motion machines would be possible. I think there is a need to make up a story of energy balance, and one such story was told in an early and compelling form by Ashtekar and Magnon-Ashtekar. They demonstrated that if the total full momentum carried by gravitational waves emitted up to some retarded instance is finite, then an asymptotic balance equation holds for every retarded time. That is, the sum of ADM energy can be expressed as the energy of this. The ADM energy can be expressed as the sum of Bondi energy and radiative energy. And here, ADM energy is the time component of ADM full momentum, which is the generator of the asymptotic spacetime translations at spatial infinity. It's measured at spatial infinity and it remains constant. Bondi energy, on the other hand, is the time component of the Bondi Sachs full momentum evaluated at the null infinity, and it decreases as gravitational waves radiate energy away. Now, if Bondi energy, ADM energy, and radiative energy are all non-negative, then this asymptotic balance equation yields a substantive physical constraint. That is, the total amount of energy that a system could possibly emit through gravitational radiation could never exceed its initial ADM energy. It turns out, however, proving ADM positivity and Bondi positivity is very difficult. Nevertheless, mathematicians made progress in the 80s. ADM positivity was proven in 1981 and Bondi positivity a little bit later. So the asymptotic balance equation provides basically an upper bound of maximal gravitational energy one can extract from a system with finite ADM energy. One might respond by saying that, well, since gravitational energy is not well defined, it actually doesn't even make sense to ask whether we can run out of gravitational energy. But I think this issue can be framed in a way that does not invoke any dubious ontology. That is, suppose we put a sticky bead apparatus far away from a binary system that emits gravitational waves. We can ask instead, can sticky beads move forever? If the answer is to be sensible, we have to appeal to energy balance. And here I drew a little diagram with sticky bees far away from the source. You have some kind of binary source that emit gravitational energy, and you can ask, okay, can we extract more energy than the system initially has? And I think the answer should be no. The sticky bees cannot move forever. Now, of course, this reasoning actually depends on asymptotic flatness and isolation, an assumption of isolation. One can imagine if we have incoming waves pumping energy to the system, then sure, sticky bees could move forever, right? On a eliminativist view, according to which energy conservation simply fails in general relativity, one may treat energy loss at the source as a genuine loss and energy gain at the detector as a genuine gain. What such a view lacks is precisely the constraint on the maximal amount of extractable energy. Now, I have argued that we need energy balance to rule out perpetual motion machines. For completeness, I'll briefly sketch the possibilities of rejecting premise 1 and premise 2. I think we can reject premise 1. As I said, a lot of things had been said in the literature with regard to premise 1, so what I'm going to say here is not completely novel, but I'm putting it in a way that I understand the problem. So we can treat the non-general covariant and non-unique character of gravitational energy as merely reflecting the absence of any preferred localization of gravitational energy. Now we need to remind ourselves that general covariance is a local requirement. Right? Locally, where you are doesn't matter, since the law is reduced to those of special relativity under suitable coordinate transformation. But non-locally, where you are does matter. If you fall into a black hole, your head and your feet will be treated differently by gravitational effects. And gravitational waves act precisely through tidal effects, non-local tidal effects. And we can, in fact, get a gauge invariant quantity if we try to average over a region of space and time much larger than the wave length of the gravitational waves, and this can be done. So you can get a gauge invariant quantity which is known as effective stress energy tensor of the field. This can be done. Then we can say in the absence of any preferred localization of gravitational energy is not a reason to reject gravitational energy. It is a reason to invoke it when weak field conditions justify it. Now, when I first presented a mini version of this talk at Western tutorial, Carlo Ravelli responded. He said, I agree with what you said about gravitational energy, but what do you mean by real? What do philosophers mean by real? And at the time I said, well, for me, in this context, to be real is just to be able to do work. And I realized my account of realism is not that sophisticated. But the good news is I don't think I need a very sophisticated account of realism here for my argument to succeed. That is, you can pick your favorite account of realism, right? Suppose your realism requires that you have a general covariant, gauge invariant, unique, localizable quantity for gravitational energy. Then, not being real on your account does not prevent it from doing work. That is, you can reject premise 2. And here's how you can retain energy balance. You can retain the energy balance equations without interpreting the pseudotensor in the balance equation or the radiative energy as representing energy carried by the gravitational field, and instead they can be interpreted as representing the maximal work that gravitational waves can do via tidal effects. So one could say that Gravitational energy, as represented by pseudotensor, is ambiguous and coordinate dependent, but when a physical situation induces a localization, the system does work. Now, what do I mean by a physical situation inducing localization? Here are two examples. One is LIGO, the other is Io, the moon of Jupiter. It has approximately 400 volcanoes, active volcanoes, because it's heated up by the tidal effects. Due to tidal heating, a lot of volcanoes in Io. Now, if we focus on work, I think familiar worries about non-uniqueness and non-covariance do disappear. As Feynman remarks in discussing pointing theorem, one can juggle the terms around to produce infinitely many pairs of energy density and flux that satisfy the same balance equation. All of them, however, will give you the same result if you ask how much work you can extract from electromagnetic field. And similarly, in GR, for a quasi-isolated body subject to external tidal fields, different gravitational pseudotensors assign different values to the interaction energy between the body and the external field. But they do agree on the rate at which tidal work is done on the body. That is, you can have a system subject to some tidal effects, and there is ambiguity about the interaction energy, right? You can assign it to this body, you can assign it to field, there's ambiguity involved. But if you ask how much work the system is doing to the other system, then no matter which pseudotensor you are using, the work done will be the same. This idea to focus on work is already present in Feynman's own way of framing of the issue. So in a 1961 letter to Victor, or Vicky Weisskopf, Feynman recalls his sticky bead argument at the Chapel Hill conference, and he said, "I was surprised to find a whole day at the conference devoted to this question, and that experts were confused. That is what comes out from looking for conserved energy tensors, etc., instead of asking, can the waves do work?" So on the eliminativist account, gravitational energy is not real, and there's no need to make up a story of balance. On my account, energy balance is not underwritten by the ontology of gravitational energy, but by a constraint on what gravitational dynamics can do. And I think Einstein himself seems to have taken a similar stance. So when confronted with differences of opinion on whether or not this pseudotensor have to be interpreted as the energy component of the gravitational field, Einstein dismisses the dispute as irrelevant, as a mere question of words. What mattered in his view is that the balance equation provides the facilitations of perspective, which constitutes the value of the conservation. What does that mean? My interpretation is just this question: is there an up bound to the word goal? And I think the answer should be yes. Now, the view I proposed here has also an interesting precedent in classical mechanics. Potential energy was not always seen as a real energy in classical mechanics. It became what Leibniz, Huygens, and Carnot called vis viva, a real living force, only when converted into another form, such as kinetic energy. Now, for gravitational energy skeptic, they can say gravitational energy becomes real only upon conversion. But you should still retain energy balance, because energy balance basically tells you how much you can convert. Conclude here. So the idea that fundamental substances can neither be created or destroyed can be traced back to pre-Socratic philosophers. This is a very compelling Parmenidean principle. Nothing comes from nothing, and similarly, nothing simply vanishes. When vis viva appeared to be lost in classical mechanics, physicists introduced friction, potential energy to account for the missing energy. Here I want to show a quote from John Sullivan, who was an early skeptic of potential energy. He said, "The notion of potential energy explains away apparent violations of principle of conservation of energy. But is not this the very reason for the importation of the notion of potential energy? Is it not a mathematical friction brought in for convenience?" Now, potential energy sticks around, and in light of special relativity, we know the total energy is the sum of the rest energy and the connected energy. Perhaps if one wants a fundamental account of gravitational energy, we still need to wait for, say, a theory of quantum gravity. But until then, energy balance serves as a heuristic. It helps us identify boundary conditions, interpret radiative phenomena, and rule out gravitational perpetual motion machines. Thank you.